The coastline is barely visible. A thin, uneven line separates sea from sky, but only just. The horizon has dissolved into a uniform gray, where distance loses definition and depth becomes unreliable. Below, the water is dark and still, absorbing what little light remains. There are no reflections, only a flat, featureless surface stretching outward into uncertainty. The aircraft descends through this muted space without resistance. Inside the cockpit, the instruments are stable. Airspeed holds steady. Engine parameters remain within normal limits. There are no alarms, no abrupt changes, nothing to suggest deviation. The descent is controlled, calculated, routine. Yet outside, there is no visual confirmation of altitude. The approach path runs over open water, aligned toward a coastal runway not yet visible. The crew maintains a descent profile based on instrument readings, cross-checking altitude against expected waypoints. The procedure is familiar. It has been flown before. But tonight, the environment offers no reference. There are no city lights beneath the aircraft, no shoreline illumination, no gradient between sky and surface. The visual cues that normally support perception, subtle contrast, shadows, texture, are absent. The sea becomes indistinguishable from the sky. Altitude, in this condition, becomes an abstraction. The aircraft continues descending. A faint haze lingers across the approach corridor, diffusing what little ambient light remains. It does not obstruct visibility entirely, but it softens edges, erases definition. The runway, still beyond sight, offers no guidance yet. The crew relies instead on instruments as trained. But instruments require interpretation, and interpretation depends on expectation. The altimeter indicates a steady descent. Vertical speed is within acceptable limits. The rate is neither aggressive nor unusually shallow. Everything appears aligned with procedure. There is no indication of urgency. Yet the aircraft is lower than it should be. The absence of external reference has begun to influence perception, not consciously, not abruptly, but gradually. Without visual cues, the human eye cannot reliably judge height over water. The surface below provides no contrast, no scale, no motion parallax. The descent continues into a space that offers no warning. Inside the cockpit, attention is divided between instruments, navigation aids, and the expected moment when the runway environment should appear ahead. There is no immediate reason to suspect deviation. The aircraft remains stable, but stability can conceal error. A subtle misjudgment, small, almost imperceptible, has already entered the sequence. Not a failure, not a breakdown, just a slight divergence between perceived altitude and actual position, the kind that does not announce itself. Seconds pass. The aircraft moves forward, descending along a path that appears correct on instruments, yet is misaligned with the terrain below. The sea remains invisible in detail, its surface merging completely with the surrounding darkness. There is no horizon now, only a uniform field of gray. The crew continues the approach. The runway should be visible soon, but it is not. The expectation of visual contact lingers just ahead, always just beyond reach. Each passing moment reinforces the assumption that the aircraft is still on profile, still within parameters. There is no immediate correction, no abrupt change in pitch or thrust, no sense of danger, only continuation. The aircraft descends further. The altimeter unwinds steadily. Numbers decrease with mechanical precision. Each reading confirms a previous assumption. The approach is progressing normally, but the margin is gone. Below, the surface of the sea remains unseen, flat, dark, and absolute. There are no waves visible from this altitude, no texture to signal proximity. The illusion is complete. Height no longer feels real. The aircraft is now critically low. Inside the cockpit, There is still no alarm. No system demands attention. The descent rate remained controlled. The engines respond normally. The navigation path appears intact. Everything functions. And yet, the aircraft continues toward a surface the crew cannot perceive. The final moments approach without escalation. There is no sudden crisis, no sharp maneuver, only a continuation of descent into an environment that offers no warning until it is too late. The sea rises invisibly to meet the aircraft, and the margin for correction no longer exists. Silence remains. In the early 1990s, regional air travel operated within a framework that balanced reliability with limitation. Short-haul routes connected smaller coastal communities to larger urban centers, often relying on aircraft and infrastructure that reflected an earlier generation of aviation technology. These routes were essential, economically and socially, but they were not always equipped with the same level of navigational precision found at major international hubs. The Seaview route was one such operation, positioned along a coastline where land met open water without gradual transition. The destination airport served as a critical link for the surrounding region. It was not isolated, but it lacked the redundancy and layered safety systems increasingly common elsewhere. Approaches into the airport frequently required aircraft to descend over water before aligning with the runway. In clear weather, the procedure was straightforward, but in marginal conditions, the environment changed completely. The airport itself was modest in design. A single primary runway extended parallel to the shoreline, with approach paths that depended on a combination of ground-based navigation aids and pilot interpretation. Precision landing systems, such as full instrument landing systems, ILS, were either limited in capability or absent entirely. Instead, crews relied on non-precision approaches. These approaches required strict adherence to altitude step-down fixes, predefined points where the aircraft must not descend below a certain altitude until reaching the next segment. Unlike precision approaches, they did not provide continuous vertical guidance. The responsibility for maintaining a safe descent profile rested largely with the flight crew. This distinction was critical. Without vertical guidance, altitude awareness became procedural rather than automated. The margin for error narrowed. Seaview's coastal geography introduced another variable, one that was less mechanical and more perceptual. Approaches conducted over water, especially at night or in low visibility, presented a well-documented hazard known as a black hole illusion. In such conditions, the absence of ground lighting or terrain features removes depth perception. Pilots may perceive themselves as being higher than they actually are, leading to an unintentional low approach. The illusion is subtle. It does not distort instruments, only the pilot's interpretation of spatial position, and it becomes more pronounced when the sky is overcast, the sea is calm and featureless, there is minimal ambient lighting, the runway is not yet visible. Seaview often met all of these conditions simultaneously. Meteorological patterns along the coastline were consistent but deceptive. Moist air moving over cooler water frequently produced haze and low-lying cloud layers. Visibility, while technically within operational limits, could degrade in quality rather than distance. Edges softened, contrast reduced, and horizons blurred. Pilots described it not as poor visibility, but as flat visibility. In this environment, the difference between sky and sea could disappear entirely. By 1994, aviation had already begun transitioning toward more advanced safety systems, but implementation was uneven. Many aircraft still relied on earlier versions of ground proximity warning systems, GPWS, which were effective in certain scenarios but limited in others, particularly during controlled, steady descents over flat terrain or water. These systems were reactive. They warned of imminent danger, but not of gradual misalignment. Air traffic control procedures at Seaview reflected the airport scale. Controllers provided standard approach clearances, but terrain separation remained the responsibility of the crew once established on final approach. Radar coverage, while present, was not always precise enough to detect small deviations in vertical profile. The system functioned on trust and procedure, training, and adherence. On the day of the accident, conditions were not considered extreme. There were no severe storms, no reported system outages, no indications that the flight would encounter anything outside normal operational parameters. The weather was described as marginal but acceptable, a category that often concealed complexity. Flights had landed successfully earlier. The approach was open. Nothing suggested that this descent would be different. The aircraft assigned to the route was part of a fleet commonly used for regional operations, reliable, well understood, and suited to short coastal flights. It was neither new nor obsolete, operating within the expected standards of the time. Maintenance records indicated no immediate concerns. The crew assigned to the flight were qualified and experienced within the operational environment. They were familiar with coastal approaches, non-precision procedures, and the specific characteristics of airports like Seaview. There was no indication of unusual workload or disruption prior to the descent. From every operational perspective, the flight fit within normal parameters, and that is what made the environment particularly unforgiving. Because the risk was not in a single failure. It was in the convergence of small, individually manageable factors. A non-precision approach, a featureless visual environment, limited vertical guidance, subtle atmospheric distortion, dependence on human interpretation. None of these elements, on their own, would have been sufficient to cause an accident. Together, they formed a condition where error could develop quietly, where deviation could remain unnoticed, where descent could continue, correct in appearance, incorrect in reality. By the time the aircraft began its final approach toward Seaview, the system surrounding it, technical, environmental, and procedural, was functioning exactly as designed. But design has limits. And on this approach, those limits were about to be tested. Understanding the Seaview accident requires separation, not of events, but of influences. Each component of the flight functioned within its expected limits. The aircraft responded correctly. The crew operated within procedure. The environment, while degraded, remained technically flyable. The systems in place provided the information they were designed to provide. The failure did not originate from a single point. It emerged from alignment. The aircraft assigned to the Seaview route was a twin-engine regional airliner typical of early 1990s operations. Designed for efficiency over short distances, it combined reliability with relatively simple avionics compared to later generations. Its flight deck was not fully digital. Instrumentation relied on a hybrid system, analog gauges supported by early electronic displays. Altitude was presented through a barometric altimeter, requiring manual interpretation and cross-checking. Vertical speed was indicated separately, without integrated predictive guidance. There was no automated vertical path management comparable to modern systems. Descent profiles had to be flown manually. The aircraft was equipped with a ground proximity warning system, GPWS, an early generation safety feature designed to alert crews when terrain closure rates became unsafe. However, its capability was limited by design. It did not see terrain ahead. It reacted to what was already happening. In steady, controlled descents, especially over flat terrain or open water, the system could remain silent until the margin for recovery was minimal. It was effective in preventing abrupt terrain collisions, but less capable in detecting gradual descent misjudgment. Navigation systems on board included standard radio-based aids, VOR, VHF Army Directional Range, DME, Distance Measuring Equipment, possibly NDB, Non-Directional Beacon, These systems provided lateral guidance and distance information, but not continuous vertical guidance. Altitude discipline remained procedural. The aircraft itself showed no mechanical irregularities prior to the approach. Engine performance, control surfaces, and instrumentation were functioning within normal parameters. There was no failure to explain the descent, only a system that required precise human interpretation. Crew. The flight crew consisted of 2 pilots operating under standard multi-crew coordination principles. Both were qualified. Both were trained for non-precision approaches. Both had prior experience in coastal operations. Their training emphasized adherence to published procedures, altitude step-down fixes, minimum descent altitudes, and missed approach criteria. They were familiar with the limitations of non-precision approaches and the importance of maintaining situational awareness in reduced visibility. But training does not eliminate perception. It only guides response. In environments where visual cues are absent or misleading, pilots must rely heavily on instruments. This increases cognitive load, not dramatically, but steadily. Attention must be divided between monitoring altitude, tracking lateral position, managing descent rate, anticipating visual acquisition of the runway. In such conditions, expectation becomes a factor. If the runway is expected to appear at a certain point, the mind begins to anticipate confirmation. Small discrepancies, slightly lower altitude, slightly earlier descent, may not immediately trigger correction if they align with expectation. This is not error in isolation. It is gradual misalignment. Crew resource management, CRM, in the early 1990s was evolving. Cross-checking procedures existed, but the assertiveness and structured challenge response culture seen in later years was not yet fully standardized across all operators. Communication remained professional, but subtle deviations could persist without immediate verbal correction if they were not clearly recognized. There is no indication of distraction, no evidence of fatigue beyond normal operational levels. The crew was functioning, but they were operating within an environment that reduced the clarity of feedback. Environment. The environment at Seaview on the day of the accident was not severe. It was deceptive. Visibility was reported within acceptable limits, but the quality of that visibility was degraded. A combination of haze and low cloud cover produced a low-contrast visual field, where edges were softened and depth perception was reduced. Over the sea, this effect intensified. Water, especially when calm, reflects minimal texture under diffuse light. Without wave contrast or reflection, it appears as a flat, uniform surface. When combined with an overcast sky, the boundary between sea and air can disappear entirely. This is the foundation of the black hole illusion. Without external reference points, altitude feels higher than it is. Descent appears shallower than reality. The approach path seems stable even when it is not. At night or in low-light conditions, this illusion becomes more pronounced. But even during daylight, under heavy haze, the effect can persist. The approach path into Seaview required extended flight over this environment. There were no terrain features beneath the aircraft to provide scale. No lights, no visual gradient, only uniform gray. The runway, when not yet visible, offered no corrective reference. The environment did not obscure the aircraft. It obscured reality. Systems. The broader aviation system surrounding the flight was functioning within its defined structure. Air traffic control provided standard approach clearance. Once established on the approach path, responsibility for terrain clearance transferred to the crew as dictated by non-precision approach procedures. There was no continuous vertical monitoring from the ground, no automated system to alert controllers of a gradual descent below profile. Navigation aids guiding the approach provided lateral alignment but limited vertical support. Without glide slope information, descent had to be managed using published altitude restrictions. timing and distance calculations, manual rate of descent adjustments. This process was inherently less forgiving than precision approaches. It required constant verification. The GPWS onboard served as a final safeguard, but only at the edge of safety margins. It was not designed to detect early-stage deviation during a controlled descent. It would not intervene until proximity became critical. In effect, the system architecture relied on layered responsibility, procedure, crew interpretation, instrument cross-checking, final warning systems. Each layer was intact, but each layer assumed accuracy in the one before it. When a small deviation entered early, unrecognized, it passed through each layer without immediate correction. By the time the final layer activated, if at all, the opportunity for recovery would be extremely limited. The Seaview approach was not inherently dangerous. The aircraft was capable. The crew was qualified. The systems were operational. The environment was within limits. But when these elements aligned under conditions of reduced perception and procedural dependence, the margin for error became narrow, quietly, progressively, and without immediate indication. The stage was set, not for sudden failure, but for descent that would appear correct until it no longer was. The descent begins as expected. The aircraft is established on approach, aligned laterally with the intended track toward Seaview. Navigation aids confirm position. Distance to the runway decreases at a predictable rate. Airspeed is stable. Configuration changes. Flaps, landing gear are introduced in sequence, each action deliberate and routine. Nothing suggests deviation. The aircraft passes the initial approach fix. Altitude is reduced in accordance with the published procedure. The descent rate remains moderate, controlled. The crew monitors their instruments, cross-checking readings against expected values. The environment outside remains unchanged, flat, gray, without definition. There is still no visual contact with the runway. This is not unusual. The approach continues. At the next step-down point, the aircraft descends again. This is where precision begins to matter more. Non-precision approaches require strict adherence to minimum altitudes at specific distances. Each segment acts as a boundary, an invisible floor beneath the aircraft. Descend too early, and the margin begins to erode. The altimeter unwinds. The aircraft continues downward. The descent profile now depends entirely on interpretation. Distance versus altitude, rate versus expectation. The navigation instruments provide lateral certainty, but vertical positioning must be managed manually. The crew believes they are on profile, but they are slightly below it. The deviation is small, not enough to trigger immediate concern, not enough to be visually apparent, only enough to matter later. The aircraft continues toward the final approach segment. The haze ahead diffuses all remaining light. The expected visual cues, the faint outline of runway lights, the suggestion of shoreline, do not appear. The horizon remains absent. The outside world offers no confirmation. Inside the cockpit, the instruments remain the primary reference. Altitude continues to decrease. The descent rate remains stable. The aircraft crosses another critical distance point. At this stage, the minimum descent altitude should act as a limit, a point where descent must stop unless the runway environment is clearly visible. But expectation interferes. The runway should be visible soon. The crew continues descending. The deviation increases. Still gradual, still controlled, still unrecognized. There is no abrupt change in aircraft attitude, no excessive sink rate, no instability. The descent appears normal, smooth, continuous, consistent with a standard approach. But the aircraft is now below the safe profile. The sea remains invisible. No texture, no movement, no indication of proximity. The altimeter continues to unwind. Numbers pass through thresholds that should trigger reassessment. But in the absence of external cues, interpretation becomes delayed. Each reading is processed within the context of expectation. The runway must be just ahead. It is not. Seconds pass. The aircraft descends further. At this altitude, any correction must be immediate and decisive, but there is no clear signal to initiate it. Then, subtle at first, a realization begins to form. Not from the outside, from within the instrument scan. Altitude is lower than expected for the given distance. The discrepancy is small, but now noticeable. A correction is considered, but time has already been lost. The descent continues for another moment. Then, a warning. The ground proximity warning system activates. Its tone is abrupt, mechanical, unmistakable. A final layer of protection, triggered not by prediction, but by proximity. The call-out breaks the continuity of the approach. Attention shifts instantly. Recognition becomes immediate. The aircraft is too low. Corrective action is initiated. Power is advanced. Pitch begins to increase. But the margin is gone. The aircraft is already within a space where recovery requires altitude that no longer exists. The sea, still unseen, is now critically close. There is no time to reestablish climb. No time to regain safe separation. Only a fraction of a second between recognition and consequence. The aircraft descends a final distance. Controlled flight. No structural failure. No loss of control. Only insufficient altitude. The surface of the water meets the aircraft without warning. The sequence ends as it began, without visual confirmation, without a clear horizon, without the moment of realization arriving soon enough. Silence returns. The first indication that something was wrong did not come from the aircraft. It came from its absence. Seaview's control tower had been expecting the aircraft to emerge from a haze on final approach. First as a distant silhouette, then as a set of landing lights aligning with the runway. That sequence never occurred. Radio contact, routine until the final moments, ceased without urgency. There was no distress call, no declared emergency, only silence where confirmation should have been. At first, uncertainty lingered. Delays on approach were not uncommon in marginal conditions. A misapproach, a holding pattern, a temporary communication lapse. Each possibility remained plausible for several minutes. But as time passed, the absence became definitive. The aircraft had not landed. Search and rescue procedures were initiated. Given the last known position, aligned with the approach path over water, the search area was immediately defined by uncertainty. There were no eyewitness reports from the ground, no visible impact site, only radar data and estimated trajectory. The sea, calm and featureless, offered no obvious sign. Initial search efforts focused along the extended center line of the runway approach. Aircraft and maritime units were deployed, scanning the water for debris, fuel sheen, or any disruption of the surface. Hours passed before the first evidence appeared. Small fragments, lightweight materials, were located floating on the water. Their distribution suggested a high-speed impact, but the pattern remained contained within a relatively narrow area. The aircraft had not broken apart in flight. It had reached the surface intact. Recovery operations were complicated by depth and visibility. The seabed beneath the approach path dropped gradually, creating a zone where wreckage could settle beyond immediate reach. Specialized equipment was required to locate and retrieve critical components. Among the priorities were the flight recorders. The cockpit voice recorder, CVR, and flight data recorder, FDR, were eventually recovered from the seabed after a coordinated effort involving sonar mapping and underwater search teams. Their condition, though affected by impact and immersion, allowed for data extraction. The investigation began with reconstruction. Flight data revealed a descent profile that appeared stable in rate but inconsistent in altitude relative to distance. The aircraft had followed a continuous descent rather than adhering strictly to the step-down altitudes defined in the approach procedure. There was no indication of mechanical failure. Engine performance remained normal until impact. Control inputs were consistent with a controlled approach. Navigation systems functioned as expected. The aircraft responded correctly to all commands. Attention turned to the sequence of altitude management. The FDR showed that the aircraft descended below the prescribed minimum altitude before reaching the point where descent was authorized. The deviation was gradual, measured not in abrupt changes, but in a steady, continuous descent that began slightly earlier than procedure allowed. This early descent was not corrected. The CVR provided additional context. Crew communication remained calm and procedural throughout the approach. Standard callouts were made, but their timing suggested a reliance on expectation rather than strict positional verification. There was no indication of confusion or disagreement in the cockpit. The approach was perceived as normal. Until the final moments. The GPWS warning was recorded. Its activation occurred seconds before impact. The crew responded immediately. Power increase, pitch adjustment, but the altitude available for recovery was insufficient. The response was correct. It was simply too late. Investigators examined environmental data. Weather reports confirmed the presence of haze and reduced contrast conditions. Visibility, while technically within limits, lacked depth cues. The sea surface was calm, with minimal texture. The horizon, as described by other pilots operating in the area, was indistinct or absent. These conditions aligned to the characteristics of the black hole illusion. A key factor in the investigation was the absence of external visual reference. Without a visible horizon or ground features, the crew's perception of altitude would have depended almost entirely on instrument interpretation. In such scenarios, even minor misjudgments, if uncorrected, can persist and compound. The approach procedure itself was also reviewed. As a non-precision approach, it required strict compliance with altitude restrictions at defined distances. There was no continuous glide path guidance to assist the crew. Vertical positioning depended on manual calculation and monitoring. Investigators identified this as a contributing factor, not a failure, but a limitation. The system assumed precision in execution. It did not enforce it. Air traffic control procedures were examined. Controllers had provided appropriate clearances based on standard operations. There was no evidence of incorrect instruction or miscommunication. Once the aircraft was established on approach, terrain clearance responsibility rested with the crew. Radar data, while useful for lateral tracking, lacked the resolution to detect subtle vertical deviation in real time. There was no ground-based intervention. The investigation concluded that the accident resulted from controlled descent below minimum safe altitude during a non-precision approach, influenced by environmental conditions that degraded visual perception. There was no single cause, only a sequence. Early descent below step-down altitude, lack of visual reference, gradual erosion of situational awareness, delayed recognition of altitude discrepancy, insufficient time for recovery after GPWS warning. Each element, individually manageable, combined into a chain that remained unbroken until impact. The findings carried implications beyond the flight itself. They highlighted a vulnerability not in machinery, but in interface, between human perception and environmental ambiguity, between procedural expectation and actual position. The aircraft had functioned. The crew had acted within their understanding. The system had operated as designed, but the design had limits. And in this case, those limits were reached without clear warning. In aviation, accidents are not endpoints. They are transitions. What ends in one moment? Flight, continuity, expectation, reappears elsewhere as analysis, revision, and change. The Seaview accident did not introduce unknown risks. It revealed existing ones with clarity that could no longer be overlooked. The lessons were not dramatic. They were precise. At the center of the findings was a familiar vulnerability, the gap between perception and reality. The investigation confirmed that even experienced crews, operating within normal parameters, could misinterpret altitude in environments where visual references were absent. This was not a failure of skill. It was a limitation of human perception. In response, the emphasis on stabilized approach criteria began to strengthen across operators. The concept was not new, but its enforcement became more structured. Crews were required to meet defined parameters, altitude, speed, descent rate, by specific points in the approach. If those parameters were not met, the response became standardized. The approach must be discontinued. No gradual correction. No continuation based on expectation. Only a missed approach. This shift reduced reliance on subjective judgment in ambiguous conditions. It replaced interpretation with defined thresholds. Technology followed a similar path. The limitations of early ground proximity warning systems became increasingly evident in accidents involving controlled descent. These systems, while effective in certain scenarios, lacked predictive awareness. They reacted. They did not anticipate. In the years following the accident, the aviation industry accelerated the adoption of enhanced ground proximity warning systems, EGPWS. Systems capable of comparing aircraft position with a stored terrain database. Unlike earlier systems, EGPWS could detect gradual descent toward terrain, unsafe approach profiles, loss of altitude relative to known geography, and it could do so earlier, with time to respond. This shift transformed terrain awareness from reactive to predictive. Approach procedures themselves were also reevaluated. Where possible, precision approaches, those providing continuous vertical guidance, were expanded. Instrument landing systems, ILS, and later satellite-based augmentation systems reduced reliance on manual altitude management. Where non-precision approaches remained necessary, guidance improved. Clearer altitude callouts, enhanced briefing requirements, greater emphasis on cross-verification between pilots. The role of crew resource management evolved as well. Communication protocols became more assertive. Ambiguity was no longer acceptable in critical phases of flight. If one pilot perceived a deviation, it had to be stated clearly, immediately, and without hesitation. The expectation shifted from cooperative monitoring to active challenge when necessary. Silence, once neutral, became a risk. Training began to incorporate scenarios specifically designed to replicate visual illusions, including the black hole effect. Pilots were exposed, in simulators, to environments where perception could not be trusted. The objective was not to eliminate illusion, but to recognize it early and rely on instruments with discipline. Awareness became a skill, not just knowledge. Air traffic control systems also saw gradual improvement. While controllers were not responsible for vertical navigation during non-precision approaches, advancements in radar and monitoring tools began to allow better detection of altitude deviations. In some environments, minimum safe altitude warning systems, MSAW, were introduced to alert controllers when aircraft descended below safe limits. These layers added redundancy, not to replace pilot responsibility, but to support it. The Seaview accident did not lead to a single sweeping reform. It contributed to a pattern, a gradual strengthening of procedures, technology, and training that, over time, reshaped how approaches were conducted in low-visibility environments. Its legacy exists not in isolation, but in integration. Today, an aircraft approaching a coastal runway under similar conditions operates within a system that has absorbed these lessons. Predictive terrain awareness, Structured approach criteria. Enhanced training for perceptual limitations. Improved communication standards. The environment remains the same. The sea still reflects no light. The horizon can still disappear. But the margin has changed. Where once small deviations could persist unnoticed, there are now multiple points of detection: procedural, technological, and human. The silence that defined the final moments of the Seaview flight has been replaced by earlier signals, clearer thresholds, more decisive responses. The aircraft never announced its deviation. The system now does, and that is where the legacy remains. Not in the moment of impact, but in the quiet adjustments that followed.